Right, so let's look at this problem here. We're dealing with a turbine. Okay, it has one inlet and two outlets. Uh, the the steam is entering the turbine at these conditions, right? P1 30 bar, T1 350 degrees Celsius, and mass flow rate of 30 kilogram per second. Some stream, process stream, is extracted at after a little bit of expansion. Some stream is extracted at these conditions. The pressure and temperature are given. The mass flow rate is not given, so it's something we may need to find out. And then the rest remains in the turbine and of course undergoes expansion, exits at a much lower pressure. Okay, so these are the values given. Pressure is given, temperature is not given, but the quality is given, and the mass flow rate is again given here. So we know how much is coming in at state 1, how much is going out at state 3. We know the conditions of what's going out at state 2, we just don't know its mass flow rate. Okay, we the stray heat transfer and effects of motion and gravity are negligible as always, so we're saying that it's an adiabatic turbine. These are the values for T naught and P naught, and for this turbine we need to do a couple of things. We need to calculate the power developed and the rate of exergy destruction, and then using those two we have to devise and evaluate its exergetic efficiency, which is again a ratio of desired output by the required input. Okay, and for a turbine, as we just discussed, the input is the decrease in the exergy for the working fluid, and the output is the work output. Right, that's the only reason why we build a turbine. Now here, I mean, since we're dealing with water or steam, we need to make use of the steam tables, and in the, I mean it the enthalpies and the entropies may or may not be given in the question. Okay, so when you're looking at steam tables or any other tables, the most crucial thing is you need to know where exactly which table to look at, right? Whether it's a compressed liquid, saturated table, or superheated vapor. So here for state 1 and state 2, the pressures and temperatures are given. So a hint is when pressure and temperature is given, it cannot be saturated mixture, right? Because pressure and temperature cannot define the state completely if it's when it's a saturated mixture, because these two are dependent on each other. So it's either compressed liquid or superheated. What do you think it is in this case? Is it superheated or is it compressed liquid that's entering at state 1 and exiting at state 2?
Superheated vapor, maybe.
Yes,
Because
it surely
he
is
said it's
superheated.
with steam entering, so.
Yeah. So steam is superheated vapor. So superheated steam, I mean, uh, I use the word steam in a rather loose manner, but looking at these conditions, it cannot be, let's say, compressed liquid. So it has to be superheated vapor, of course. And I mean, that's what we do in a turbine, right? So sometimes you may get, if you're not sure, if you cannot look at the conditions and figure out for yourself what tables to look at, go and figure out what the saturation temperature is and then see if it should be compressed liquid or not. But in a turbine, we never send in a compressed liquid. We always send superheated vapor because that's what we are sort of expanding. Okay, so you can use your intuition and go directly to that table and save yourself some time. For the last case, state 3, okay, the quality is given, the quality and pressure is given. So it's obvious that it's a saturated mixture. Okay, so you can go to the tables and determine all these values for enthalpy and entropy. Now we will be required to determine the enthalpy and entropy values in a lot of problems that we solve in this course, right? And you have to do that in your homeworks and also in exams. So that was one of the reasons why I gave you the practice quiz. But since a lot of students did not actually attempt it, so what I'm going to do is I'm going to give one question from practice quiz in quiz 1. Okay, so there's going to be, maybe you have to calculate enthalpy, maybe you have to calculate the mixture property or something. It'll be one of the questions from there. So make sure you go through and do the practice quiz. It's just a bonus that I'm telling you beforehand. But yeah, you should know how to use the property tables, right? If you don't know, you're gonna struggle. Okay, now come back to this. Let's come back to this problem. We have just 4 minutes, so let's try and do the first part at least. We need to determine the power developed, okay, in this turbine. Any ideas? How can we do that? You guys did this in 203. All we need is a power output from the turbine. How do we start? Guys, the starting is the difficult part. If you get it, then you can solve the problem. If you don't get it, then it's gone. Think of it in a simple manner. Just relax and think. What sort of look, when you're dealing with these sort of systems, you always are dealing with balances, right? You have to put some sort of a balance here. What do you think it is?
Energy balance.
Yes, energy balance. Excellent. We just have to put in the energy balance here, right? So let's use the energy balance. So here for this particular thing, I mean, it's a steady state, steady flow system that we always know. So energy in has to be equal to energy out. Now, there are different ways in which energy can come in. Either it can come in and as heat, but we know there's no heat coming in or going out. So I will not write Q in, or let me just write Q in and it gets cancelled. There's no work input in a turbine, right? It produces some work. So there is work output. Apart from heat and work, it can come in through the mass, right? So what's coming in is simply, it's coming in at state 1, so m dot 1 h1. Now this is all that's the energy that's coming in. Now energy that's going out, well, there's absolutely no q dot out. We said heat losses are 0. There is some amount of work being done. That's the work output, which is what we need to determine, plus m dot 2 h2 plus m dot 3 h3. Okay, we have h1, h2, h3 given here. We have m dot 1, m dot 3, okay, given in the question. We don't have m dot 2. We need to determine m dot 2. How do we determine m dot 2?
It will be 5.
Exactly, from simple mass balance, right? So m dot 1 is m dot 2 plus m dot 3 from simple mass balance, simply because m dot n has to be equal to m dot out. And you know the values, right? M dot 3 is 25, m dot 1 is 30, so it has, the balance goes out at 2. All right, so the work output would simply be m dot 1 h1 minus m dot 2 h2 minus m dot 3 h3. Okay. Now we have everything that we need. It's just a matter of plugging in the numbers. Once you plug it in, I've plugged in the numbers on the slides on the on the blackboard, but here let me just put in the numbers. Let me put in the final answer. It comes out to be about let me see, should be about yeah, 2014. Yes, so it comes out to be 20,139.5 kilowatt. Okay, now we want the answer in megawatts. You just have to divide it by 1,000, so it's 20.14 megawatt. Okay, so this part is from 203. The part from 204 is Exergy destruction. How do we determine that? We'll look at it in the next class. Any questions, let me know. Otherwise, that's the end of the class, and we'll meet on Thursday, inshallah. The power developed is simply something that you guys have been doing before. It's simply a matter of applying the energy balance. Okay, you apply energy balance to the turbine and you get the power developed. Now, as far as rate of Exergy destruction goes, there are two ways to go about it, right? There are two methods to determine that. So we'll just talk about both methods, right? So the power developed is something that comes simply from energy balance, as we discussed in the last class. And this is the value of power developed that we calculate. Remember that since it was given that we had to provide the answer in megawatt, we had to sort of convert the kilowatt to megawatt. So make sure you do that conversion based on what's asked in the question. If it's not in the same units, you will lose some partial grade. So now coming back to the Exergy destruction. Now, when you want to calculate Exergy destruction, there are basically two ways of doing that. Okay, one way is to make use of the Exergy balance equation that we are looking on the screen right now. So in this particular example, there's no heat loss to the surroundings, so the first term goes down to 0. Okay, we have some work output and we have some change in flow exergy of the fluid as it enters and exits the system. Also, there's some Exergy destruction here. All right. So the value of work output is already calculated in earlier, right? We just calculated the power developed. We said it's 20.14 something megawatt, right? The exergy specific flow exergy changes between inlet and exit are something that we can calculate simply by making use of the information given and getting the enthalpy and entropy changes. I'll put in the formula in a bit, so we will see exactly how to do that. And once you have the changes in flow exergy as well as the work output, we can easily calculate the exergy destruction because that will be the only remaining unknown in this equation. So let's send exergy destruction to this other side and rewrite this equation. So it's going to look like minus work output plus the mass flow rate and the specific flow exergy associated with the entry, and then what's happening at the exit. Now, you have one inlet to exit, so it's not a simple matter of calculating the specific flow exergy changes between the two states. You have to sort of you have three states here, right? So what we do is we evaluate EF1 individually, EF1, EF2, EF3 individually. So when you're evaluating the specific flow exergy, you evaluate it with the reference of the environment. So H0, T0, and S0, and these are all values that you pick up based on the temperature and pressure given for the environment. All right. So this is the expanded form of EF1, EF2, EF3, and once you combine the terms for H0, you will see that it basically gets cancelled out because it comes at H0 times m.1 minus m.2 minus m.3. So this part is simply zero from the energy balance, from the mass balance, and same way these get cancelled out. And then this part right here is is basically m.h1 minus m.h2 minus m.h3, indicating the enthalpy change within the turbine. And this basically is equal to, it's numerically equal to the work output. All right. So you have basically minus w.cv plus w.cv, and therefore these two also get cancelled. Ultimately, after a lot of these terms, after lots of things getting cancelled, what we are left with is simply the term related to entropy changes, which is this right here. Maybe I'll use a green ink. So I'm talking about this term right here. This is the only thing that remains, and that's what we have here. T0 times this entropy changes. And the values of S1, S2, and S3 are already given here, right? We have the values, or you can pick them up also from the property tables for steam. And once you plug them in, this is the value that you get. It again comes out to be 4,496 kilowatt or 4.5 megawatt. Okay. Now, as is obvious here, this is a pretty long way, right? So this is not, I would not say this is the most recommended way for doing it. It is a good way, and you may need to use this way depending on the information that's given in the question. For example, if I give you the power output and also I give you the value of EF1, EF2, EF3, this is probably the easiest way to implement the exergy balance and calculate exergy destruction, right? In this specific case, well, it becomes a little bit longer, right? So you have other shorter ways. So this is one way of getting it. There's also another way of getting exergy destruction. So let's look at the other way, okay? The other method that we can get exergy destruction is simply by multiplying the entropy generation sigma with the value of T0. And here T0 needs to be in Kelvin, okay? So how do we get entropy generation? Well, you just need to use entropy balance, okay? Now, entropy balance term or entropy balance equation for an open system, the general equation is given by this formula right here. But for a turbine, we are dealing with a steady state, steady flow system. And for a steady state, steady flow system, we know that properties do not change within the control volume with time, right? So this part, the change of entropy of the control volume with time would be zero. And here, since we're assuming that there's no heat loss to the surroundings, this term also goes down to zero. So we're just left with these three terms right here. Okay, or we are left with sigma dot is equal to summation of MESC minus summation of MISI. I refers to in, or inlet, E refers to exit. All right. So we have two exits, one inlet. We can just write that down here. And this is what it comes out to be, right? So M2S2 plus M3S3 are the two exits minus M1S1. Okay, so this is sigma dot. We are just not looking for sigma dot, we're looking for exergy destruction. All right, so exergy destruction is T naught times sigma dot, or T naught of course needs to be in Kelvin, and here the value of T naught is 25, so you convert that into Kelvin, that's 298 Kelvin times the values. All right, so what are the values for m dot 2? Well, m dot 2 we said that was 5 kilogram per second, so S2 is here, plus m dot 3 is 25 into S3 is here, minus m dot 1, it's 30 into S1 is right here. Okay, so again, when you do the calculation, you realize that it comes out to be the same number, right? It basically is the same number that we had calculated, 4.5 megawatt. So this is the second way and the more easier way for calculating entropy generation, specifically in this problem and a lot of similar problems. All right, so you start from, so therefore it's sort of important to also understand entropy balance, and as long as you're comfortable with entropy balance, it's a very simple way. It's a very simple method to go and calculate it. And as you will notice, what we are calculating here, right, T naught times the entropy changes is exactly what we did in the last in the previous method. This is what we ended up with here as well. But to reach to this point, we had to sort of cancel out a lot of other terms, right? Or even if you would calculate all of those, would numerically be equal to cancel out among themselves. So this is these are the two different methods, and it's your choice which one you want to use. Both are fine with me. Any questions till now?
Clear, doctor.
Okay, great. So then we have looked at part A and we have solved it, right? So we got the mass at state 2 from the mass balance. We calculated the power output and also the exergy destruction. Now we need to do part B, which is to devise and evaluate exergetic efficiency. Now, when we say devise and evaluate exergetic efficiency, what we are saying is that you need to start from the exergy balance equation, okay, which is this for a steady state system, and you need to then calculate the value of exergetic efficiency, which basically is written in the form of the desired output by required input. Okay, but here the input and the outputs are based on the terms you get from the exergy balance equation. So these are in terms of the exergy changes. Okay, so whenever you're given this question of devise and evaluate exergetic efficiency, you start with the exergy balance equation and then you go on till you identify the desired output and the required input terms. Okay, now in this question, again, as we said, there's no heat loss to the surroundings. The first term goes down to 0. Okay, we have one inlet, so here this is in, and we have two exits. Okay, these are the exit terms. So for this specific problem that we're dealing with, one inlet to exit turbine, this is how the equation would look like. Okay, so work output plus m dot 1 EF1 minus the two exits minus exergy destruction. Now we need to rearrange this equation. All right, we need to rearrange this equation in the form of input is equal to output, and then we can sort of decide what is the desired output. Okay, so I'll keep these things on one side, and I'll send the other, that is the work output and the exergy destruction, to the other side. So once you rearrange the equation, this is how it's going to look like. You have the change in exergy of the fluid or of the steam here, which is equal to the work output of the turbine plus exergy destruction. Okay. Now, in this particular example for a turbine, right, the main reason why we build a turbine is because we want to get some power output out of it, right? The work done or the rate of work is our desired output. Okay, but at the same time, we need to provide some input to it. And in a turbine, the input is basically the the steam or the working fluid coming in at a high enthalpy and high exergy. So the change in exergy of the steam is what is the input that we need to provide, or it's basically the cost that we are paying for it, right? So this term on the left here, or the left hand side, is basically the net exergy input, or this is the simply the input that we are providing. Okay, so this is basically what's being used to provide the work output. So exergetic efficiency, which is simply in the terms of desired output by input, can be written in this format where this is the work output and this is the numerator, the denominator is the input or the net exergy input that we are providing. Now here again we have two choices. Either you can go ahead and calculate this exergy change of the fluid between inlet and exit, or you could use a very simple method, which is basically use this rearranged equation, exergy balance equation, and see that this term on the left is equal to the summation of work output plus exergy destruction. So the denominator, I can simply, instead of calculating these three terms, I could just replace it with the work output plus exergy destruction as we get from this equation 1 here. Okay, so work output and exergy destruction are exactly what we calculated in part A. So then it becomes very simple. I don't have to do any more calculations. I just have to plug in the numbers. The power output we said is 20.14 megawatt. The exergy destruction came out to be 4.5, and that's it. That's as simple as plugging in the numbers, and we get the exergetic efficiency of 82 or 81.73% here, which is very good.